So very similar to the problem we saw in the last example here for number 25, page 269, we have the function k of x. It is equal to negative 2 times the quantity 12x squared plus 5 raised to the power of negative 6. So notice here that what is inside the parentheses, that is the expression, that is the number, that is the base that is raised to the exponent negative 6. So again, anytime we are looking to take the derivative here and we notice that we might be working with a composite function, why do we think it's a composite function? It's because, again, we can almost just view this, what's inside the parentheses here, as its own little mini function. And for this here, 12x squared plus 5, we can view that as the function that is being fed inside of another function, defining it to be a composite function. So what does that make the outside function? Again, if we're thinking about a composite function as an outside function and an inside function, it might be a little, might not be too technical there, might be a little tasteless for some, but again, just the idea that we're working with two functions, one on the inside, one on the outside. Well, now we can almost view this, again, this function g of x as just some number. This is just some number within parentheses, which makes our outside function here minus 2 times some number with the exponent negative 6. So our outside function is here, and our inside function is here. So we go on to take the derivative using the chain rule. We want to use the chain rule when we're working with a composite function. So here, our notation, k prime of x, taking our derivative here, we're going to start on the outside. We're going to work with the outside function f of x, take its derivative first. So just treat all of this like it's just some number, like it's the variable x. Exponent negative 6, we're going to now invoke the power rule. Take the exponent and multiply it out front. Negative 6 times negative 2 is a positive 12. We're treating this as the variable, so this stays the same, 12x squared plus 5. But now what are we supposed to do using the power rule? We want to subtract 1 from the exponent. Negative 6 minus 1 is negative 7. Now that we have taken the derivative of the outside of our function, we will now take the derivative of the inside of the function. Taking the derivative of 12x squared plus 5, well, 12x squared, its derivative becomes 24x. 12 times 2 is the 24. Subtract 1 from the 2, we get x to the first power, which is simply x. The derivative of a constant, the derivative of plus 5, remember, the derivative of any constant, plus 5, minus 7, minus 2, minus pi, it's always 0. So this just goes away. We're left with one term in our derivative, 24x. Take a look here at what our derivative is. We have essentially 3 factors here. In the numerator, we have 12. We have the factor 12x squared plus 5 to the negative 7 power. And then in parentheses over there, we have the 24x. Well, again, notice that middle expression, that middle factor, has a negative exponent. And so to make this a proper looking function, let's go ahead and turn that negative exponent into a positive exponent by using the reciprocal rule of exponents. If you have a negative exponent in the numerator, you can make that negative exponent positive by placing that factor into a denominator. So this 12x squared plus 5, when we place it into the denominator, that negative 7 exponent becomes positive 7. And so here we are left with, in our numerator, 12 times 24x. Well, we go into our calculator there and multiply together 12 and 24, and we get 288. Of course, this factor of x, it is a factor, so it stays attached in terms of multiplication. Our derivative, k prime of x, is equal to the rational function, 288x divided by 12x squared plus 5 quantity to the power of 7. So looking at problem 28 on page 269, 4.3 exercises, a little bit different than the previous 2 exercises, but we're going to see same logic applies here when we use our chain rule and ultimately when we use our power rule. We see here we have a function f of t, so switching up the variable a little bit, and instead of taking the derivative with respect to x, we will take our derivative with respect to the variable t. So we have here 8 times the square root of 4t squared plus 7. Now we're looking at this and we're thinking, okay, what's going on here? We now have the square root symbol. But again, notice that we have almost staring right back at us another little mini function, if you will, underneath our radical sign. Notice right there we have 4t squared plus 7. So let's try this out here. Let's see what happens if we define this to be g of x. Well, again, if whatever is under our radical sign, if that's just some number, then it's just a number. We can treat it like a variable. We can almost just treat it like x. And also, really quickly, I apologize. We are not using a variable x. We are using t in this case here. Let's go ahead and keep it very consistent there. So in this case, we're working with g of t. Now, what would our outside function be if this was just a number? Well, again, I keep in mind here that if we just change all of this to a variable, what are we left with? We have this function here that looks like 8 times the square root of t. Well, that's a nice looking function. That's a square root function. So notice our outside function, when we look at this in terms of a composite function, our outside function is the square root function. Our inside function, what we're feeding into our radical function, well, that's a quadratic. So again, our input is a quadratic function. We're feeding it into a radical, into a square root function, and we're going to get an output that is a real number, or at least we hope so. So once again here, when we take this derivative, we want to think about this in terms of a composite function. Therefore, we need to use the chain rule. But how can we take the derivative of the square root? Keep in mind how we did it in our previous examples, in our previous sections. When you have a square root function, all we know to use right now is the power rule. Keep in mind that a square root can be rewritten as a rational exponent. If we have exponents, we have powers of a variable, we have power functions, so we can use our power rule. So what we're going to do here is we are going to rewrite this function f of t as 8 times 4t squared plus 7 to the 1/2 power. Remember that the square root sign is the rational exponent 1/2. Now we see that we have 8 times t to the 1/2 power. We can use our power rule. Moving forward with the chain rule, taking the derivative of the outside function, here is our exponent. So we will take the exponent and multiply it out front. 8 times 1/2. Well, 8 times 1/2 is the same as 8 divided by 2. So taking our derivative here, f prime of t, 1/2 times 8, we get 4. Keeping the inside of the parentheses exactly the same, 4t squared plus 7. But now we're subtracting 1 from 1/2. 1/2 minus 1, well, that's a minus 1/2. Now we need to go inside the parentheses and take the derivative of our mini function, our smaller function. Of course, this is going to be with multiplication. Taking the derivative of 4t squared plus 7, 2 times 4 is 8. Subtract 1 from the exponent, you're just left with 8t. Taking the derivative of a constant, keep in mind, is just going to give us 0, so that goes away. So the derivative of 4t squared plus 7, we're left with just the 8t. So there is our derivative. But again, we have this negative exponent. We can clear up this expression just a little bit nicer by taking this base that has the negative exponent. We will throw that into our denominator. But what happens here? The negative 1/2 exponent becomes a positive 1/2 exponent. And what does the positive 1/2 exponent indicate? It indicates a square root. So basically what we're doing here is we're taking something that has the square root attached to it, negative exponent, we're going to move it down to the denominator, and we're going to take the square root of it down in the denominator. What's left in the numerator here? 4 times 8t, which gives us 32t. So our derivative here is the rational function 32t divided by the square root of 4t squared plus 7. So this begins the section on 4.3, the chain rule, page 262. The chain rule is the rule that we like to use when we are working with composite functions. So recall that a composite function is a function composed of another function. Normally with functions, we plug in a number, but with composite functions, we plug in another function, which is essentially another number. So let's look at this rule here. It says here, if y is defined as a composite function, f of g of x, then the derivative is f prime of g of x multiplied to g prime of x. Now, what does that mean here exactly? Well, it says that for our outside function f of x, if we take the derivative of the outside function composed of our function g of x, Then we'll go in and we'll take the derivative of g of x and multiply that derivative to f prime of x. So essentially we're taking two derivatives where we start on the outside of the function and then we move our way to the inside of the function. Now let's think about that here with our example from page 269, 4.3 exercises. For number 22 here, we're being told to find the derivative. It says here for our following function, we have y equals, notice here we're taking the fifth power here of the quantity 2x cubed plus 9x. So here we have the quantity 2x cubed plus 9x, and all of that is raised to the fifth power. Now, how can we view this as a composite function? Well, if you notice here for this function, it's almost like you can view what's in parentheses here. Let that be the g of x function. So we see here that we have some equation, some function y. Again, we can just call this f of x if we wanted to. Now, right now, we're going to use the notation of y, but notice that, and not to get this confused, let's call this h of x for right now. So we have some function out here that is composed of a function. So what is this outside function, we might think? We have some number in here raised to the fifth power. So it's almost like this outside function here, we can treat this as some number to the fifth power, or in other words, x to the fifth power. So our outside function here, it looks like it's x to the fifth power, but that function is composed of another function, 2x cubed plus 9x. Now, if we wanted to take the derivative of this composite function, let's think about this here. Let's use our notation here. We are taking the derivative of our equation y, dy, with respect to the variable x. So again, our derivative notation here for the equation y is dy over dx. Well, using our chain rule here, again, this is the alternate form on page 266, just a little bit easier to look at notation-wise. It says here for our composite function, first take the derivative of the outside function. So if we're treating this outside function as x to the fifth power, now using our power rule there, that's 5x to the fourth power, right? Take the exponent, move it out front, and then subtract 1 from the exponent. But here, we won't get 5x to the fourth power because what is this inside function here? It is now 2x cubed plus 9x. All of that was raised to the fifth power, but now we're going to subtract 1 from the exponent and we will get 4. So again, just notice here that we had some number to the fifth power, some number here to the fifth power, taking the derivative of some number to the fifth power, moving the 5 out front, and subtracting 1 from the exponent, we now have half of our derivative. But what does it say to do here now? Go inside of the function here, look at g of x, and take its derivative. And whatever you get from that derivative, multiply it. So we're going to look here at 2x cubed plus 9x. We want to take the derivative of this inside function here. Well, we look at 2x cubed and using our power rule, multiplying the 3 and the 2, we get a 6. And then subtracting 1 from the exponent, that becomes a 2. So derivative of 2x cubed, 6x squared. Now the positive 9x here, anytime we have that linear term right there, the 9x, all we're doing is essentially dropping the variable x. So taking the derivative of 9x is simply 9. And that would be our derivative here. Taking the derivative of the outside first, and then multiplying that by the derivative of the inside. And if you would like to clean this up, it is not necessary, but some things we like to look at here is that since our constant or our factor that is a coefficient is out front, we can move the next smallest term or factor out front, rather the next smallest factor, 6x squared plus 9. And then the largest factor we see here is that factor to the fourth power, 2x cubed plus 9x to the fourth power. And there we have our derivative. All right, we're looking at problem number 32, page 269, 4.3 exercises. We're being told to find the derivative. Now we have here x cubed plus 2 multiply the quantity x squared minus 1 to the fourth power. Now we have a lot going on here, but we're being told to find the derivative. And we're working out of 4.3, the chain rule. Now, keep in mind that when we introduce new topics and new properties, new rules, we might have to keep, reaching back into previous sections to use them. And notice here what we said. We are multiplying here, right? X cubed plus 2 is multiplying the x squared minus 1 to the fourth power. So we will have to use our product rule here. That's where we want to start off. We will use our product rule for these two factors, but when we deal with the derivative of this factor here, notice that's where the chain rule is going to come into play. So let's go ahead and try it out. dy over dx, taking the derivative of y with respect to the variable x. Okay, so our product rule here, again, if you need to pause the video and go back and look at the previous notes, our product rule says here, take the derivative of the first factor and multiply it to the second factor. Add that to the first factor multiplied to the derivative of the second. That's what we're going to do here. Derivative of our first factor is 3x squared. And now we're going to multiply that to our second factor, x squared minus 1 to the fourth power. We will add this to our first factor, multiplied to the derivative of our second. Now keep in mind here, for the derivative of the second factor, we will need to use our chain rule. So x squared minus 1 is the function that's being fed into our larger function, which we see here could be x to the fourth power. Some number is being raised to the fourth power. So some variable to the fourth power. We use our power rule here. We're going to take the exponent and move it out front. It becomes a factor. That looks pretty messy. All right, there's our factor 4. X squared minus 1 stays the same. Now we'll subtract 1 from the exponent and we'll get 3 there. So there we have our derivative, but it looks pretty messy, right? We can clean this up a little bit here. And let's start by noticing that there are some common factors here. So what is our greatest common factor? Well, again, here's our plus sign, right? This is our first term and this is our second. Now, why are these our only two terms? It's because all of this is multiplying here. These are just the factors that make up a term. Here are the factors. And look at this, excuse me. I took the derivative here and I never finished by taking this derivative. We took the outside derivative, but now let's take the inside of the derivative. X squared minus 1, that derivative there is 2x. We didn't finish the chain rule there. Shame on me, shame. So let's go ahead and finish this out here. Notice that we actually do have some common factors present. For the first term here, there's a factor of x. And here we have a factor of x. Moreover, notice that there are 4 factors of x squared minus 1 here, and there are 3 factors of x squared minus 1 here. So we can factor out 3 of those because they're common for both terms. So factoring out the x and factoring out the 3 common factors of x squared minus 1, let's look at what we have left behind here. For the first term, we leave behind a 3x, which is multiplying the leftover factor of x squared minus 1. Our second term, what did we leave behind here? Well, just to get the constant out in front, or the coefficient, this 4 and this 2, they're factors, so they multiply to give us the factor of 8. Now, these 3 factors of x squared minus 1 got moved out here, so we're left here with the x cubed plus 2. So here we have our greatest common factor, but now here we need to clean this up. It looks a little muddied. So again, within the brackets, let's look to simplify. We have our distributive property here and here that we want to use to get rid of those parentheses there. So just working within the brackets here, distributing the 3x, we get 3x cubed minus 3x. Distributing the 8, we get 8x cubed plus 16. So our derivative here, dy dx, see if we can still see me on the screen. Let's go ahead and skip this down here. Dy dx is equal to the product of the GCF, x, and x squared minus 1 to the third power. And now simplifying in the brackets, 3x cubed plus 8x cubed, we get 11x cubed minus 3x plus 16. And so our derivative is the product of those 5 factors. So in the previous example, we saw where we could combine the efforts of using the chain rule, the product rule, and the power rule. Let's look at this example here, problem 38. We have the function p of t is equal to the rational quantity 2t plus 3 cubed divided by 4t squared minus 1. Notice again here that we are starting off with a rational function. Now, we could be creative here. We could get creative and we could take that factor in our denominator and we could move it to the numerator by giving this entire expression the exponent -1. Now, we're going to go ahead and keep it here as a rational because we want to use the quotient rule for derivatives to find the derivative here for problem 38. Notice again how we're going to combine all of this together here. For our numerator, we have a composite function. Move the hands there. We have a composite function. And then overall, we have a quotient. So we need to use our quotient rule. We need to use our chain rule. And then as always, we need to use our power rule. Go ahead and start it off here. Let's recall that the derivative for a quotient says we're going to take the derivative of the numerator first. So taking the derivative of our numerator, using the chain rule, moving the exponent out front, what's in parentheses stays the same. Subtract 1 from the exponent. But now go inside the parentheses and take the derivative of 2t plus 3, which is just 2. So we take the derivative of the numerator, but now we multiply that to our denominator, 4t squared minus 1. But now it says here to subtract. I'm going to move the screen just a little bit. Sorry for any noise. We are now going to subtract the product of the numerator so the product of the numerator and the derivative of the denominator, which we get to be 8t. All of this will be divided by the denominator raised to the second power. There is our derivative. But once again, that derivative sure looks pretty messy. So what we want to do here is focus on simplifying our numerator. And the first step we want to think about when simplifying the numerator is their greatest common factor. Well, let's go ahead and scan through this problem here. And as we look, we notice that this 2t plus 3 is over here and it's over here. There are 2 factors of it here. There are 3 factors of it here. So we can factor out 2 of those. So let's go ahead and move out 2 of those factors. 2t plus 3 squared. So 2 of those we can move out. Also notice here, there's a factor of 8 and a factor of 2. 8 is even, so we can factor a 2 out of that. And this 2 right here, we can go ahead and move it out front as well. So we're going to take that coefficient factor and move it all the way to the front. And there we have our GCF. Our GCF is the 2, and the 2 factors of 2t plus 3 all multiplied together. So what do we leave behind here in our numerator? Well, in the numerator, we leave behind the 3 and the 4t squared minus 1. We are subtracting, well, what do we leave behind here? We took out a factor of 2 here, so we leave behind a factor of 4. We leave behind a factor of t, and we left behind one of these factors of 2t plus 3. Again, we are only focused here on simplifying the numerator because our denominator, it's fine. It's just the denominator squared. The numerator is where we want to clean this up. Simplifying the numerator right now. So take a look at that there and see how we can simplify what is in our bracket. Once again here, we want to take a look at distributing the 3 to the 4t squared minus 1. And we want to distribute the -4t to the 2t plus 3. Let's try that out there. Our GCF, it's remaining the same for right now. But right here, we distribute the 3 and get 12t squared minus 3. But what happens when we distribute the -4t squared? We get a -8t squared, minus 4t times positive 2t is -8t squared. Minus 4t times positive 3 is minus 12t. So our numerator here is the GCF 2 times 2t plus 3 squared multiplied to what this simplifies out. 12t squared minus 8t squared is 4t squared minus 12t. minus 3. All of this is over the our denominator here, which is 4t squared minus 1, quantity squared. This is p prime of t. Again, in order to find this derivative here, p prime of t, we had to use 3 different rules here. We had to start off by using our quotient rule, and while we were using the quotient rule, we invoked both the power rule and the chain rule. So here, problem 54, exercise 4.3, page 269. We are looking here at an application where we are to assume that the total revenue for the sale of X TV sets is given by the following function. We have here R of X is equal to 24 times the quantity X squared plus X to the 2/3 power. We're being tasked with finding the marginal revenue when 100 TV sets are sold. Now keep in mind that marginal revenue is the exact revenue for a specified number of TV sets. So here, for 100 TV sets, what is the exact revenue? Or the exact rate of change for the revenue? In this case here, well, we need to pick our derivative. For R of X, if we find R prime of X, that will give us the function for marginal revenue. So let's go ahead and try that out here. R prime of X. So what do we think we need to do here? If you take a look at it and you look back to our chain rule definition or our chain rule form, we see that once again we have some expression raised to the 2/3 power. So we have this power here, just like the power rule. We can invoke that property as well. So let's go ahead and try that out here. We have our exponent 2/3. Let's move that out front and multiply, right? We take the exponent, move it out front with multiplication. 24 times 2/3. Well, 24 times 2 is 48, and 48 divided by 3 is 16. So when we multiply the 24 times the 2/3, we get 16. We're going to leave what's inside parentheses the same. And now when we subtract 1 from our exponent here, 2/3 minus 1 is the same thing as 2/3 minus 3/3, and we get negative 1/3. Now we need to go inside parentheses and take the derivative of the inside function. Again, it's composite, so now we go to the inside. We take the derivative of x squared plus x, which is 2x plus 1. Move the 2 out front and subtract 1. Derivative of x, just drop the x, the coefficient is 1. We can clean this up a little bit by taking this factor with the negative exponent and placing it in the denominator. So R prime of x, our marginal revenue here, is the factor of 16, multiply the factor 2x plus 1, and this is all divided by x squared plus x to the 1/3 power. But remember that if the 1/2 power is the square root, the 1/3 power is the cubic root. So when we take this negative 1/3 and move this factor down here, it becomes positive 1/3, and thus we can write it as the cubic root of x squared plus x. And there we have our formula for marginal revenue. But now it's saying find the marginal revenue when 100 TV sets are sold. So because x represents the number of TV sets, we're going to take 100 here and plug it into R prime of x. If they wanted to know the revenue of 100 TV sets, we use our revenue function. But for marginal revenue, we use the marginal revenue function by inputting the 100. So here, R prime of 100, inputting the 100 to R of x, becomes 16 multiply 2 times 100 plus 1. This is all divided by the cubic root of 100 squared plus 100. Now again, this will be very time consuming to try to work all this out on our own. So let's make sure that we do have a nice calculator alongside us as we are working these types of applications. And we see here that by simplifying this down, we get that the marginal revenue for the sale of 100 TV sets, again, rounded to 2 decimal places because we are talking about pennies on the dollar, rounds to approximately $148.78. Our marginal revenue